break. So welcome back to our session. We'll continue with our session deep learning with PyTorch, and we will discuss about today classification with PyTorch. And classification can be of different kind, and it involves predicting classes into one or many classes. And we have binary, multi-class, and multi-level classification. Oh, there is echo. Can you hear me now?
Yes.
Is it echoing?
Yes. It is not.
Yes. It's okay.
Okay, from my side, it's not.
Okay.
It's not echoing.
Okay, what about now? Is it okay echoing now or not?
It's okay, doctor.
It is okay. It is not okay.
Okay. Malama Saada, is it echoing from your own end?
I think so. Let me rejoin.
Okay. So, we have binary classification, multi-class, and multi-level classification. So binary classification, given an email, classified into, for example, spam or not spam. This is binary because we have two things. Multi-class classification, when you have many classes, because here we have two classes, not spam and SWAT 2, binary. But here we have, for example, multiple classes. So let's assume we want to classify tweet into either positive, negative, and neutral, meaning we have 3 classes, or 4 or 5. That is called multi-class classification. So we have this. But we also have what is called multi-level classification. So when you have something, it has different kind of levels. So for example, as give an example, when we want to classify a disease, a particular disease, a disease has different symptoms, right? Symptoms 1, 2, 3, 4. All those systems belong to one disease. That is called multi-level classification. So we'll be able to see this kind of different classification in this session. But before we see the coding part, let's look at the general architecture of classification neural network. So we have different kind of hyperparameters: input layer, hidden layer, neuron hidden layer, output layer, hidden layer activation, output activation, loss function optimizers. So let's look at discuss each of these before we go and start coding. So what is input layer? So we see this is our input layer, right? This is input layer, and the input layer are your features. So when you have your data, those features are the input layers. You can see here same as number of features. For example, age, sex. If you have a data with age, sex, all these are features, and now they will be imputed here. Now the next one is then we call this input feature in Python in futures. In futures means input features. You see that when we come to start coding, we call in futures. Now we have hidden layers. So these are hidden layers. Here is hidden layer. So a neural network can have at least one hidden layer. So here we have one hidden layer, but as you know, we can have multiple hidden layers, right? We can have multiple hidden layers. We can say hidden layers. In neural network, we can have multiple ones, images. So you can see here we have hidden layer 1, hidden layer 2. So you can have multiple hidden. That's why it's called hyperparameter. So all this stuff are hyperparameter. It depends on your stuff. Neurons per hidden layer, and you can see problem specific. So what does it mean? So here in this hidden layer, you can see we have 1 neuron, 2, 3, 4. We can see we have 4 neurons. You can see here we have 4 neurons, right? And you can have as much as neuron possible. You can see this is a neuron. You have many, you can see many neurons. So this is also called hyperparameter. So we'll discuss about that one. But generally from 10 to 512. So sometimes we have 10 to 512. But we have what we call output layer. So what is output layer? This is output layer. We can see, you see output layer here because we are doing binary. So you can see we have 1, 2 output binary. So this is output layer. So the output layer, how it can be in binary classification, in multi-class, it can be 1 per class, and here it can be 1 class or the other. Hidden activation layer. So you can see here we have what we call, and we have what is called activation layers, and we have hidden activation layer, we have output activation layer. So what is the meaning of this? So it means activation layer, we have 2 kinds of activation layer. We have activation layer at hidden layer. We also have activation layer at output, activation function at what? Output layer. You can see this is F. So what we mean here is like, we have a value comes here to this neuron. We have bias comes here. They are here. Now here we have a function that act on this summation. So let me show this. And here, activation layer summation. Let me show you something like this. All right. Yes. So look at it. Can you see this is a weight? You have an input. We have weight comes here. We have weight comes here. We have weight. Now, when we sum this one with the bias maybe comes here. Then before we pass this summation to the next layer, we have what we call activation function that will act on this one. Yes. Okay. Yeah. This is the one I wanted to. Yeah. Look at this one. This is the one I want. So you can see here we have the weight. We have weight. Now this weight, you can see we have weight times x, because what we are imputing here is what? X, right? X. But remember here we have weights that will pass for each one here. This is a weight, and plus bias. So you can see here weight times x1. So for each one, for x1, we'll say x1 times the weight here, x times weight plus b bias. So bias will come. So you can see. But before we pass this summation to the next one, we will have what we call activation function that will act on this summation to give us to the next output. So here, that is what we call, can you see the function? Or called hidden activation function. Hidden activation function. Now in the output layer also, we have another activation function, which is also called output activation. So you can see hidden activation, output activation. So usually in hidden activation, we have what we call ReLU. We have in output activation, we have what we call sigmoid. So you see in binary class, we use ReLU. Also in multi-class, we use ReLU. Output activation function, here we use softmax, here we use sigmoid. So you see, we need to understand this different kind of activation function so that we use them when the problem, when you are using binary classification, this is this. When you are using multi-classification, this is this. Then the last one, loss function. We have what we call loss function. I will go a little bit on these ones, or we have also optimizer. So let me, now we understand all these, architecture. Now let's see this. The choice of activation function in the hidden layer control how the network learn training data. So we have different kind of activation functions, we'll see, and the choice define how the network learn the data. But the choice of activation function in the output layer define the typical prediction, the model. So if you are doing, two things, for example, we can use sigmoid. If we are using, multiple things, we can use softmax. We'll see that. There are many activation in the hidden layer, and sometimes activation is called transfer function, squashing function, non-linearity function. All these are called the name of activation function. Any question? Before we go, any question? Okay, so activation function for the hidden layer. So what kind of activation function do we use in here? So one of the most widely used activation function in hidden layer is ReLU. What is called ReLU. And we use activation function. So here, if I have at this layer activation function, we use generally the same activation layer in each layer. So in each layer. So in hidden layer, we use maybe one activation function. In the second hidden layer, we use the same activation. So we use the same activation function in different layers. So in different hidden layers. So that's why all hidden layers typically use the same function, activation function. It is unusual to use different one. Okay, so you see, these are some of the activation function, sigmoid, 10H, ReLU. So you can see them. What is now the sigmoid? What is 10H? What is ReLU? Who can tell us what is sigmoid is doing from this graph? What is sigmoid doing? Anybody can tell us? Who can tell us what 10H is doing? Who can tell us what ReLU is doing here? Don't forget here, like when you have the sum, everything you sum them here, then this function, you map it, you apply the function on the summation here, and it gives you the output. So this function is mapping to some values because that is the summation of all this. So now what it's doing, this function is different kind of function. We have sigmoid, we have 10H, we have the ReLU. So who can volunteer for sigmoid? Zaradin, what sigmoid is doing? Okay.
Normally
so we can
for sigmoid, it is normally taking the range for trying to minimize the values from -1 to 1. The values must be from -1 to 1. That, if I'm not mistaken, the range for sigma.
So who can tell us ReLU? Who can volunteer ReLU? In I am mathematics, where is the mathematics people? ReLU, this is mathematics. What is ReLU doing with this function given X? So let's look at it.
Normally for ReLU, it is normally taking all the negatives to 0.
Okay, so let's look at it.
From 0 to positive. Yeah, there will be no negative in ReLU.
So ReLU is defined as function that returns 0 if the input is less than 0 and return at the input if it is greater than 0. So you can see ReLU. If something is negative, can you see negative? We don't have negative. If you are the summation here, if what we sum here, the whole what we sum here give us -1, then if we apply ReLU, it will return 0. But if the sum of this one give us 3, that is greater than 0, then the function ReLU will return 3. That is what it means here. You can see ReLU. ReLU is defined as a function that returns 0 if the input is less than 0, and returns the input if it is greater than 0. So you can see this activation function is used in the hidden layers of the neural network, and it helps to introduce nonlinearity. So we will discuss what is called nonlinearity in the future. But just understand that ReLU, if something is less than 0, it returns 0. But if it's greater, it returns that number. So what about sigmoid? So this is a sigmoid. So sigmoid activation function transform input value into the range of 0 to 1. So you can see here, the top one here, you can see.
I have made a mistake. Okay, it's from 0 to 1.
Yes, you can see from top here is 1. The value is maximum is 1, but you can see there is nothing. Everything that is greater than 0, they just squash it to 0. So your value is 0 to 1. Can you see 0 to 1? Can you see 0 to 1? But you can see ReLU is 0 to any number. Here we have 10 because maybe let's assume the maximum number we have is 10. If it is 1 million, it's 0 to 1 million, something like if the number is negative. What about 10H? This function takes any real value number and squash it into real between -1 and 1. So this one, if the sum of this value, we can see it here, which means that negative value are squashed between the range of -1 to 0 and positive value are squashed between 0 to 1. So this is
gives the definition of 10H as that of sigmoid.
Yeah. So if you have the sum of this value, the sum here, if the sum here, you sum them is -1. So it means that the value will be squashed between 0 to -1. And if it is greater than 1, the value will be squashed from 0 to 1. So you can see this is just kind of some mathematical functions. Deeply inside, they are doing some very useful things, which we'll see in the later on in this section, which it means they introduce what we call non-linearity. Because without them, the deep learning will not learn anything. Just put this in your mind. These mathematical functions, is very beautiful in the sense that these mathematical functions let you understand or learn some stuff. So this is what we call activation functions. So at this hidden layer, just assume, remember, in hidden layer, we have what we call hidden layer activation. And this hidden layer activation, we have what we call ReLU, we have sigmoid, we have 10H. But the most widely used hidden layer activation is called ReLU. Yes. Okay, any question before we move on? We have other variant, leaky ReLU, we have this, but let's move on. Any other question? Now, also, what kind of activation function in hidden layer are you going to use? So if you are using multi-layer for assessment, usually we use ReLU. If we are using convolutional neural network, we usually use ReLU. But if you are using recurrent neural network, RNN, then the hidden layer is sometimes, sigmoid or 10H activation function. So this is hidden layer. So if you are using, just normal multi-layer perceptron or CNN, then we use ReLU. But this one, other one, we use this one. Okay. Any question before we move on? I just want to, lay the general foundation on, the understanding before we move on to the coding part. Any question about hidden layer activation function? Or somebody want to add something? Okay, so I think we can move on. Now, let's look at the activation function at the output layer. So what about the activation function at the output layer? So we said that we have different kind of activation function also at output layer, which is this. So here, let's look at it. Okay, and the activation function for the output layer. the activation function for the outer layer depends on the type of problem we are doing. So it depends on the kind of prediction. Now, when you are predicting one value, when you are predicting two value, what kind of value? Then your prediction type determine which kind of activation layer are you going to use at output. So we can see the output layer is a layer in the neural network that model that directly output prediction. So let's look at them. We have, for example, most widely three. We have what we call linear. We have sigmoid as well. We have softmax. So let me show us softmax. What is this softmax is? So when we do prediction, we'll see shortly, we will have some kind of output layer. It gives us this value. So when you do a prediction, the output layer finally gives you this kind of value, 1, 3, 5, 1. So, but this kind of values, they are not useful in the sense that we will not be useful into defining our classes. So we apply what we call softmax activation function, which will return this into probability, change this value into probabilities. So you can have probability. When you sum them, it gives you one. And from here, you can see this is, some of the options you can take. So this, basically the softmax activation function return the output layer to probabilities. We have linear activation function. We have what we call sigmoid as well, which we already defined. We return them into 0 to 1. So basically, these are some of the widely used, activation function at the output layer. But naturally, sometimes we basically use softmax because it returns probability. We see the detail of this as well. So this has also some of the, if you have classification, if it is binary, use sigmoid. You can see sigmoid. If you have binary classification, if you have it multi-class, use softmax. If you have multi-level, use sigmoid activation. If we are doing linear regression, then use linear activation function. So what we are saying here, you can see the activation function we use at the output depend on the problem we are talking about. So that's why here you can see we made mention here that output activation, you can see we use sigmoid if it is binary, right? Because why do we use sigmoid? Sigmoid, who can tell us why we use sigmoid in binary classification? Because sigmoid returns the value into 0 and 1.
0 and 1.
So because it's binary, so if anything is less than 0, the value is less than 0, it put in 0. If it is greater than 0, 0.5, it put it. So this is where we have sigmoid. But softmax brings you probability. So if you have 3 classes, 4 classes, it gives you the probability so that you can select the most quite often. So you can see the output layer depend on the kind of your application. So here we have binary class sigmoid, multi-class softmax, multi-level. We use also sigmoid, and the regression we linear. Now we understand output layer, hidden activation. Then the last one, loss function and optimizer. So yeah, any question before we move on? Okay, so we now understand loss function. So we have what we call loss function. We already discussed this. If you have your predictions, you need to find the difference between true and the prediction, which is called loss functions. And now, you know to use optimizer, right? And to do this. So now what kind of optimizer do we use in deep learning? So in deep learning, optimizer is used to update the parameters of the neural network to minimize the loss function. So this optimizer, we know it update the weight, right, to minimize this loss. But common optimizers in deep learning includes SGD, which is called stochastic gradient descent, ADAM, RMS probe, and ADA-grad. So all these are common optimizers. So you see, when we come to doing PyTorch, sometimes we'll put SGD, stochastic gradient. We'll say, no, use ADAM, use RMS probe, use ADA-grad, meaning there are a lot of, optimizers that the main thing they do is just to, optimize the weight, to change the weight so that the next prediction will be, the loss will be small. That is optimized. So you can see we'll be using SGD. So whenever you see we use SGD, it means stochastic gradient descent, which is basically an optimization algorithm. Yes, of course, mathematician here will know what optimization, we all know what is optimization, right? In our mathematics, when we talk about optimization problem, we are always trying to, optimize the values to some kind of stuff. Okay, then the last one, now we discuss optimizer, then the loss. So we have different kind of, you can see here, I have what we call loss function. Here I have what is called loss score. Now, what is the difference between loss function and loss score? So when you do prediction, and now you have to target, when you find the difference between prediction and the target, this result is what we call loss function. Loss is called loss. But this one here is, okay, what we call, cost function. So here you can see loss function is measure how well a given algorithm is performing in a given task. Then we have loss function and cost function. A loss function is for single training example. So when I have single training example, it's called loss function. But when I have, on that is the average loss of the entire training data set. So when I, finish everything, I finish, I finish training my model, the last score is called cost function. So sometimes this, you see the little, we have two things, loss function and cost function. So when you do prediction, you have loss function. When you finish, you go, and you finish the last one, that is called cost function. That is for the whole data set you optimize. That is called cost data. Now, so what kind of loss function do we use now in deep learning? Now we see in optimizer, there are many, SGD, ADAM, RMS, but what kind of algorithm do we use to find the loss? So this also loss function depend on the problem you are working on. If you are working on regression, we have MSE, we have MAE, we have Huber loss. If you are using regression, that is mean square error, mean absolute error. If you are using classification, we have binary cross entropy, we have categorical cross entropy. So you can see the loss function here we are talking about is not something constant that you will always be using 1, 1, 1. No. It depends on solely on the problem you are working on. Yeah, any question?
So for this loss function, are they limited to this, like for regression, we have like root mean square error?
Yes. We have RMSE. It's just like
in PyTorch, are they limited to this, or we can apply?
No. We have different of them. Just this is
so that is
introduction.
Because it is PyTorch, that
yeah.
is why.
Yeah, so you can see regression, classification, autoencoder, we are killed. But if you are using GAN, these are some of the common laws. Just to tell you, the idea is just to tell you we are not using a single function. Yeah, just to tell you. So now we understand, I think we understand the whole of this deep learning architecture. So let's start moving on how we can do that code. Any question before we move on? Okay, so we're gonna use create a toy data set that we are going to use. So here you can see sklearn and import what is called make cycle, which is the data set. Now we can see when I run this, okay, make cycle, what is make cycle? So you see in Python, we can use help to see whether something is an object, class, or function to see that. So this make a large cycle containing a smaller cycle in 2D. So this is a data set that allows us to make a large cycle with smaller cycle in a 2D. And you can see it has different parameters. N sample. What is n sample? Integer or tuple. If integer, it is a tuple number of point generated. If two element number of point in outer cycle and inner cycle. So these are some of the stuff. Yeah. So you can also use question mark if you want to find some help about the function. So you can see make sample. By default, we have 100. You have shuffle, noise, random, some stuff like that. Make a large cycle of content in there. So let's look at how we can create a cycle. So here you can see I say the number of sample is 1000. So how do I know this make cycle has argument n sample? You can see here when I call this n cycle, this is the argument, some stuff like that. So we can see here I create the okay, import the data here. Okay, right. So we are creating the data set that we use. So here I create X. So here I create Y, because this make cycle, what it returns two values, right? This is X, this is Y. So here we have X and this is Y. Don't confuse why we are using this data set. We are using this data set just for explanatory purpose to see how we can do classification. You can see here we have X. So we have two features. You can see 1, 2. And now we have Y, which is one feature. So we can see here for giving these features and this 1, 2, this is the value is 1. For giving the second one, this is the value for the y. So that's what we mean. So we can see what is the length of x and y. So you can see both the x and y, they are 1,000 samples. So we have 1,000 sample. Remember here length and shows us the length of the, so we have 1,000 sample each one. Here we can see we are talking to the 5 fans sample, first 5. So you can see the first 5 sample for the x, and now here the first 5 sample for the target. So you can see this target, given this one, this is the target value. This given this one, this is the target value. So given these 5 sample, these are the answers, right? Now let's take this y and x and put them in pandas. So you can see here we call PD the data frame, x column. So x whole row, but the first column. So you can see this is my x, right? This is my x. Now when I do like this, who can tell me what will be returned here? What will be returned here? Salisu, what will be returned here if I do like this?
First column.
First column, right? So let's look at. So this, can you see it give us the first column? When I do, what about this? If I do like, what will it give us?
The second.
It will give us the second column. So this is what I'm trying to do. Because when we say this, you know, when I say this, it means the whole row. This means first column. Well, it means the whole row, second column. So here you can see I'm assigning x1 because this is how we create pandas. You remember pandas data frame. If you want to create pandas data frame, you can use this. I'm giving this. So this is x2. This, so you can see this is one. And the level, you can see this is the level, and this is the value of y. So you can see here we now create a data frame from the cycles data. And now we want to use this. This is one feature, second feature, this is our predictive value. So we want to train a models to do this. Yes, so we want to, here we plot the data. So you can see here the X, Y, and now the C. So what is the meaning of this? So you can see here, okay, can somebody explain this scatter plot for us? I know this is just Python, it's not nothing about PyTorch. Okay, so what I'm trying to do here is, you know, the x-axis here, the first column, this is the x, and you can see the y. This is also the second column value, I put it the y, and here the color here to be the y value, this y value. And now here we visualize. So in essence, what we are trying to say, this is what the data looks like when you plot it. So you can see we have the bigger plot and we have the inner plot, inner cycle. So we use this data to try to do some kind of classification, just to classify red cycle and, you know, blue cycle. So we want to train a deep learning whether it can classify this problem. So here, that's why we just create the data. And when you are creating this kind of data, this is what we call toy data. When you are trying to do some stuff, it's called toy data, right? Yeah. Okay. Right. Any question? Okay, so what about data? Checking the input share. Let's look at the input share. So our data, we have input X, we have Y, right? So we can see here, the X is 1,000 row and 2 column. So what about this one? Well, who can tell us? We have something, just a number and comma and this. What is the meaning of this? Who can tell us?
It's a scalar value.
It's a scalar value. What do you mean it's a scalar value?
Meaning just one column.
One column.
Yes.
Okay. So why do we, yes, you are right. It means only one column. So in Python, what do you call this? Something with just comma and the other thing is different. What do you call this?
The features that are target.
Yes, I mean, yeah, this is a target. but we have only one, we put one, so okay. So now here is X. So let's look at this. This is X, you know, it's X. We have, you know, we can say here we have 1,000 row, right? And we have 2 column, right? But what about Y? We know Y is only one value, which is this, right? Something like this, only 1 column, right? And 1,000 row. Now, what I'm trying to say is for us to understand is, this is how we represent it, right? This is what we call what in Python? Tuple. Do you remember tuple in Python?
Okay, tuple. Oh,
Do you remember tuple in Python?
Tuple, yeah,
Yes.
tuple is dictionary. Yeah.
So in Python, basically, if that is what we call a tuple. A tuple is basically a number. You know, if you have 1, you don't put something like this. So let me show you something like this. Anyway, let's move on. We are already in Python, but just to show you, like here means we have 1,000 row, only 1 column. Yeah, and also if you want to see like how many item do we have in this stuff, you can call x.shop. You index the first element, it will give you 1,000. So it means in this X we have 1,000 element, 1,000 row. Yes. Okay, so yeah, so that's what I just want to share you about that. So let's move on. Okay, so let's turn our data into tensors. So it means now we have our, you know, X and Y, but before we do anything with it in PyTorch, we must turn it into what tensors, right? So let's import torch. Here is our torch. Now let's see what is our data. Already our X and Y and X are already in NumPy array, right? And yeah, so who can tell me what is the difference between type and D type here? What is the difference between these two things? What is the difference between type that I call type here and call D type here? What is the difference between the two?
The first one is for the first one is for the dimension, while the second one is for the data type.
Dimension, is that correct?
Are they not doing the same thing?
I think doctor is the size difference.
The
Size?
Yes, byte.
because there are 2 types. The first one is ND array, and the second one is data type float system.
Right. So we can see this one is telling us when we call this type, it's telling us what type is this. It tells us it's NumPy. What type? This is telling us what type is X is, because we have different kind of type. It can be tensor, it can be NumPy array, it can be, you know,
A list.
So it tells us this is a NumPy. This one tells us which type of data type is, because NumPy array is not a data type. Do you understand what I mean? Here it tells us which kind of data type is float 64. It can be float 32, it can be float 16, it can be, do you understand what I mean?
Yeah. Understood.
I'm not sure if I'm understood the difference between, like, you know, you can see this type, it tells us this is a NumPy. It doesn't tell us
because there may
type.
be a situation whereby type X may be tensor.
Yeah, exactly. Yes. So yeah, so we can see now how can we convert these guys from NumPy. So you can see torch, we have a function torch from NumPy X, we type convert them to float. So here we convert them to float. So why do we convert them to to torch? Is basically when you want to do deep learning, we convert all our futures to tensors, because PyTorch work with tensors. So PyTorch is basically a library that consists of, which is a tensor library, is deep learning library, is also autograd library. So we can say this PyTorch is of, you know, library that consists of, it's a tensor library, also deep learning library, and also automatic differentiation. What do you call differentiation mathematics? How do you call it? Auto grad? Anyway, auto grad. We'll come out to this. So PyTorch is basically tensor library, deep learning library. So what do I mean by tensor library? You can do a lot of things in tensor deep learning library. It implement deep learning stuff that we, an autograd, it do what we call automatic differentiation, which we will see. So now we can see here, yes.
Doctor, I have a question here.
Yeah.
But if this function from NumPy,
Yes.
if you first X, is it not going to convert it to the default data type? Is it necessary that we must do dot type?
Good question.
The error.
Target error?
Yeah. Expected dot tensor.
So let me answer your question. So here, let's look at this. We expect it to return something. So his question is, why do we need to call type? Because it will automatically convert it to type for the PyTorch float 32. So let's look at this. What this is an expected np array got tensor, right? No. I made a mistake. Just wait. Let me go back. Your question is valid. Let me go back where I create, because I already changed them. Why do we create the excess? Okay, yes. Okay, let me quickly go back. Okay, we have import touch. Okay, I have my, okay, these are, they are now in ND array, right? So my X and Y, they are already ND. So we want to do this. His question is, do we need to call this to do this, say convert to float this one? Why can't we do this? Of course. So when we do this, of course, you can see it, we convert it to, let's look at it. Can you see convert to touch? So you can see type. We can see this is touch tensor, we convert it. But what type of data type is this? So let's look at this as the D type. We can see it's float 64, right? Meaning when you do this, by default, NumPy data type is float 64 by default. NumPy data type, because this is, but in deep learning, this is very important, the question he asks. Who asked this question? In deep learning, we don't actually work with float 64 because this is it consumes a lot of space, and our model will not be faster. So in deep learning, we basically work with float 32 or float even 16 or float 8, because we want to be faster and we don't want to in terms of space. So that's why you can see here it works. We import it, but when we import it, convert it from NumPy to Torch, it will come to the port Torch with default. Since it is in NumPy float 64, therefore it will be float 64 also in Torch. But we don't want that. So that's why here we said Torch.plot. And when we run this, I already converted it to tensor, my X already. Okay, let me go back and run them again. Yeah, okay, this is the X. Okay. Right. So let me import torch. Here is import torch. So here, this is my type, numpy array. So when I run on this, so you can see this is a torch, X is a torch. Let's look at what kind of type is this. The D type. Can you see it's float 32?
Yes.
So calling this one torch.plot changes it to 32. But using this only, it take the data type is hard in NumPy and just move with it. But we don't want to do that because in PyTorch, the default calculation we do even in PyTorch is just in float 32. I don't know if this answers your question.
Yes.
Okay, cool. Any question? Yeah, so you can see everything here now is in float 32, you know. And now let's divide our data. So we have Xtrain and Xn. So let's run this guy from scikit-learn. We already know what this is doing, train test split. Now here our X and Y, random size, random state. Now here, this is our data. The training Xtrain is 800, X test is 200, Y train is 800. Yeah. Now here we create the data. Now we will start building model. Any question? Any question? Shamsuddin, any question?
No, doctor, what question?
Okay, so let's move on and build a model. So we already leverage our understanding we did in last week on how we build a model. So for you to build a model, the first thing you need to do is set up device agnostic. Meaning if you are running on Colab, because what we are doing now is deep learning. A lot of things will not work on your computer. So you need to move into Colab where you have GPU, because this model, what you are doing deep learning, cannot be trained on computer sometimes. So you need to set up device agnostic. So this is the first one. So here, if we have CUDA, then we create a device. So everything now is in device. Now, when we create this device, it means you need to push your data set, all this data set, you need to push them onto this device to go into CUDA if there is CUDA. And also, if you create a model, you need to push the model to be in device, which is CUDA if there is CUDA. So let's move on. So here we already have our extent. So let's look at now, because I already create a device here. Can we see the device? Now I have a device. Now let's see Xtrain. My Xtrain, on which device is it? So I call a device here, Xtrain device. It is in CPU. Can we see that it is CPU? But we need to push them into GPU. Okay, let's move on. Where am I? Okay, yes. So you can do a lot of things to push your data into GPU. How do we push Xtrain to GPU? Who can tell me how can we put our value X to GPU? I can see X equals to. How can I send it to GPU? My X, this value. How can I send this value to GPU? Remember now it's in already. I just tried to see it. Let's assume I have a GPU. How can I send it to GPU? Because by default, when we create our X, it's already in CPU. And you see, like, I didn't send any X to CPU. I just create my device. If I'm having a GPU, now it means now device is GPU. My device is GPU. Now, how can you send your value to GPU? Who can tell us?
Xtrain.2.
X what?
First device. Xtrain.
Xtrain.
.2.
Dot 2.
Then we first device.
Then we pass device. Exactly. So we pass device like this.
Yes.
Okay. So when we run this, so it means our Xtrain. If we have GPU, if we run GPU when we run this, then we will see. If we see Xtrain the device. If we have GPU, then we see this type will be GPU. But now because I don't have GPU, that's why you see like it is still CPU. Who can, any question? Okay, any question? Right. So
Doctor,
yes.
which device is the default device?
Yes. So the default device in your computer.
Always.
Yeah. So always in your computer, what is your computer supporting? What does your computer support by default?
Is CPU.
Yes. So the default device is CPU.
Okay.
Yes. Any question again? Okay. So if there's no question, let's continue. So now, now let's create the next one is, what we need gonna do is consider a model subclassing, right? So we already remember this one in PyTorch when we did last class session. We are creating a class called model v0, and we are subclassing it from NN module, and we define init self, we define this. Now we have two layers. We are creating two layers. The first layer, NN layer, input feature, because our data said how many features? 2 features. Then the output features is 5. What this is telling us, 5 features. Remember here, we have this example. Now, if I have now 1, 2, 3, 4. Here I have 4 features. Now you can now define how many next hidden layer you want. So hidden layer, you can define any number you want. Like here they have 3. So you can define you have 6, 7, 8, whatsoever. So that's what we are doing here. In this NN layer, output features. But one thing we should know, the output feature, if we have 2 layers here, now we have 2 hidden layer. This is the first hidden layer, layer 1. This is the second hidden layer, layer 2. But the next hidden layer must have, the input feature must be the output feature here. You understand what I mean? Now here, the output feature is 1 because we want to do binary classification, we want to do. So this is what we call, how you input your layer. And this is a forward pass. And you can see in the forward pass, the output of layer 1 is now passed into what? Layer 2. So you can see here, we said self.layer 1 x is now, because we need to have layer 1, then layer 2, right? Now you can see the layer 1, the input will be the first layer. That is a forward pass. Remember, this is a forward pass. You need to do this one, then this one. So we go from layer 1, then we go to layer 2, then we have output. So here, layer 1, then we go to layer 2, and the layer 2 will return the result. This is how we define the forward pass. And remember, if we create our class, we can instantiate an object, model 0, we can see model. But remember, I told you that we need to push the model to device to GPU if we have. So here we said to device, right? And here is model 0. So we can see here, as Shamsuddin the last time he asked, why do we don't, call forward method here to create the model? So that's one good thing with OOP here. It abstract all those stuff. You can just create instantiate our object. And so we can see here, this is our model, layer 1, layer 2. And so you can see this is known as having 5 hidden unit and or neuron. So you can see I have 5 this is the first layer. We have input features, and in the first layer, the neuron I have is 5 neuron, and that neuron must be, if they are output of this layer, must be the input of this layer. Yes, so this is something we discussed. And here, this is a good explanation, which is from Playground TensorFlow. Let's look at this. Playground TensorFlow. So you can see this is an example to show us how those stuff work. So you can see this is your feature, right? Remember here, the data set we are talking about is this cycle data. You can see this is a data with a point here, and there is another one here. Now, this is a infit feature, right? And we can have neurons. You can see neurons, 1, 2, 3, 4. Now, let me add one so you can see. So here I have infit feature X1 and X2, and I have 5 neurons. So you can see the example we are showing here. Input feature 2 and 5 neurons, the output, you can see it, we have 5 neurons, right? And now how many layers do I have? I have 2 hidden layers. So you can see the 5. So you can see here, I have 5 hidden, 5, you can see is 5, input is 5, and now the output is 1. So we can see here the output. So now let's assume we are doing classification, and you can choose a problem classification, and you can choose the activation function. When we are doing classification, what kind of activation function we said is in binary classification. So we can go back here and see what kind of activation function we said we are doing.
Sigmoid, right?
Which kind of activation function?
Is
Sigmoid. So
sigmoid.
So sigmoid. When I select sigmoid
0,
here,
0, or 1.
yes, exactly. You are right. You are right. Sigmoid. And now here I have a learner rate. So learner rate tells you how fast your model can converge. So let's look this very small number. And now let's me. So can you see it's moving slow? It's doing small. It's not moving faster because I put very small learner rate. Can you see at weight? Can you see weight is doing? Can you see the weight is moving?
It's updating.
It's updating. Exactly. Exactly. Can you see the weight? But let me see, this is too small. Let me change the line rate to 0.1. Let's look at it. Okay, let me change the line rate to 0.1. And let me use ReLU, not sigmoid. Now let me run it. Look at it. Let me use 10 Let me use linear. Look at the training loss is 0.490. It means it is not doing a good job to do the classification of this because this is the training loss. Can you see that? But let me change to sigmoid. You can see the training loss illusion. You can see it perfectly classified, Can you see this?
Because it is meant for classification.
Exactly. You can see the sigmoid now classify the data.
0.0.
Look at the training loss. Yes.
Almost
Yes.
0.
Look at the test loss, 0.02. And now look at the weight. These are the weight we are talking about. Can you see these are the weight we are talking about?
And the training and test is and test loss vary. The margin is just 0.0.
Yes. Yeah. Oh, look at it.
Training
Now perfect.
loss, no, 0.
Yeah, reaching in 0. So you can see here. Yeah. So this is what we talk about learning rate. This learning rate is just hyperparameter that specify how fast this epoch is going, And these are some of other regularization that we haven't discussed, but you can also add neurons. So you can see here, I have more neurons. Can you see that? So the more neurons, the faster it converges, the deep learning, because if you have very large data, so yeah. So that's why you can see this very large neural network. So for example, this what we have GPT-3 or ChatGPT, you can see like they have 175 billion parameters. You can see how many parameters now you have, very like 2, 3, 4, 5, But now these giant models, GPT-3, you will hear they are having like 170 billion parameters. So you see like, this kind of complex stuff is what makes it to learn more things. But when you have very few parameters, it may not learn very well. But when you have very many parameters, many parameters, then the model will learn complex stuff. So the more parameters you have, the more complex your model will learn stuff. Yeah. I don't know if this makes sense.
Yeah.
So this is what we have here. Our model. So this is what we have here. You can see the input features, the output feature. So the output feature of one layer must be the input feature of the next layer, because we can see here, if we go back here, because I have like, the input, 5 here, can you see? So here I have also 5. So that's what we mean by here. Okay, so any question again?
Doctor,
Now, yes.
so is that step is just specifying the hidden layers?
Exactly. Yes. So you need to, because this is hyperparameter, it's you, it depends on you how you want. So it depends on you to define how many features you want. So if you want the features to be 20, you can say this is 20, and you can have 20 here. Do you understand? So you something like that. So it just, you need this, you need to specify the number of layers you want, and this is you that you specify that. And so this this allow the model to learn pattern from 5 numbers rather than 2 numbers. So because here we say we have 5 input features, it means you allow the model to learn patterns from 5 numbers input instead of 2 numbers. We also say that the number of hidden unit you can use in neural network layer is hyperparameter. So you can see the number of hidden unit is you can choose the way you like, and there is no set in stone value you have to use. Generally, more is better, but there are also such as too much. The amount you choose will depend on your model and the data set you are working on. So if your data set is very complex, you can select many so that it can learn complex. Since our data is small and simple, we'll keep it simple. So you can see this is telling us, since our data set is small, so we keep it simple to use the simple stuff. Okay. But there is also what we call NN sequential. So you can see here, we define this, we use this stuff like this, right? We use this stuff, everything here, but we can also use this something like this just to define our model. NN sequential, we have our NN layer, we have input features, output features, NN layer, input feature, output feature. Then here we send the model 0 to device, and now here you can see our model. But look at this one here, this implementation. We define class, right? Called cycle model this, and now we create forward pass this, and now we create the model, we instantiate an object, a model, and now put the model to see to device. Now this is a model. You can see this is the output. While we do everything here, create the class, you can see the output. But what about this one that we say is still the same? Let's take it this guy to here. Look at this guy. No, not you guy. This guy. So let's look at this. This is something very, so you can see, instead for you to define class and do whatsoever, look at another alternative, NN sequential. It allows you to do the same thing, less complex in some, if somebody, is afraid of class. So you can use NN sequential. NN sequential, you just define the layer. And now you send the model here. We just send the model, can you see the model to device? And now this is, you can see the output is still the same.
Okay. We don't need to do all that.
Yes. So this is choice one can do, but let's look at it. You can also use the same NN sequential. NN will perform forward pass computation of the input data through the layer in the order they appear. So you can see in the order they appear here, in the order, you can do this one and you can do this one. But sometimes when you are doing some complex stuff, you don't want to do the order they appear, because that is what we call skip connection, resonate. You want to skip one layer to go to the next layer. So if you use this sequential, you will not have the opportunity to do that. But if your model already is sequential, then you can use this one. So NN sequential is fantastic for straightforward computation. However, as the name says, it is always run in sequential order. So if something else happened, rather than just forward, you will want to define your own custom NN model. So if you want to do some stuff which is not sequential, you want to define your own custom subclass. So what this is saying, yes, you can use this one, but sometimes this is flexible because you need to define several things, which I also mentioned, some kind of skip connection. So yeah. Yet another sequential. So just to make sure like we understand whenever we use, so NN sequential, you can use another one which is called ordered collections. You can see NN sequential ordered diction. So this is just to give you a flavor whenever you see them. Sometimes you can see now that I'm giving you the third option. You can see ordered, like in form of order. You can see convolutional one. Then you have the first input. Then you remember for each layer, we have the ReLU, right? We have hidden activation. So for this layer, this is the hidden activation. For this layer, this is the hidden activation, but it is in form of ordered dictionary. So you have this, you know, the first one, the second one, but look at this one. NN, then you have ReLU, NN, ReLU. We'll come to this one, but just telling you that there is even another way in which you can have this, which is ordered dictionary. So anyway, I believe now we understand that, this is what we call NN sequential, and sometimes you will be seeing NN sequential, sometimes you will be seeing this implementation. All of them are still correct, but this implementation give you more flexibility to do a lot of other stuff. So this is a question that somebody will ask in PyTorch forum. I'm proficient enough to understand how to read PyTorch code and implement them to fit my need. But being self-taught, there are still a lot of things I do not understand. Trust to be told, I didn't do a lot of OOP all before learning PyTorch. I mainly just made many functions and chained them together to make my network. Since I started to look at the people's code to learn PyTorch, I have noted that there are two major ways of coding your network. One way is to stop all the layers in NN sequential and just assign that to a model, which is this. You can see that, which is what we do. Just stop everything here to NN sequential. And just assign to a model, or define a class, then assign to a model. So you can see here, we define a class, then we assign to a model. You can see to an object, you can see this one. So his question, that's, his question. My question is, what is the major difference? I have tried both the ways, and in my own opinion, NS sequential is easier. I've also seen NS sequential define within the model class as well. So this is one of the terrific, you can use whatever fit your case. While some people like to use NS sequential approach a lot, I usually just use it for small sub-models. I like to define my model in a functional way. That is to derive from NN model and write forward myself. This approach gives you more flexibility in my opinion, since you are able to easily create skip connection, etc. On the other hand, if you just want to stack layers together, just use NS sequential. So just to tell you that we'll be using in the future, just using NS sequential or using this one is still the same. So this is something that really helpful and you. So this is the NN sequential. And now, since we have our model NN sequential, let's look at what our model learns. So we know, it's still time. So let me quickly stop before we move on. So we already know state dict. State dict give us the weight of the model, what the model learns. So we can see when we create the model now here, we create the model 0, we create the model, and now we create state dict. Now, since we define our model, it has 2 input features and output features. And, the second layer, 5 input and output 1. Then we can see when we call model the state dict, the PyTorch give us some values, which are already created by the PyTorch itself. Remember, when we are training deep learning, we start with weight, random weight. And our main goal is to update those weights to find a weight that fits the model we are trying to fit the data. Now, this data, this point, we are not the one that create them. It is PyTorch that create them this way automatically because you want to start model training. So when you create a model in PyTorch, it create the model, it assign weight, which is randomly. Our goal is how can we change these weights so that they will fit our data and give us a very something good. So you can see weight 1, weight 0, because we have first layer, you can see weight 0. And how many tensors do we have? We can see 1, 2, 3, 4, 5, 6, 7, 8, 10. So because we have input feature 2 and output feature 5, 2 by 10, that's why you have this weight, 10 weight. And how many bias do we have? Because we have bias through. So because we have you have features, output features, output feature is 5. That is why we have 5 bias. And now here we have the second layer, which is 1. We can see 1 layer. And now how many weight should we have? Because 5 times 1 is 5. So that's why we have, you can see weight 1, 1, 2, 3, 4, 5. And now how many bias we have? Because of we have 1 output feature, then we have 1 bias. So you can see all these weights, they are, created by PyTorch automatically for us. Now, when we start training this model, our goal is to, given any data set, our goal is to update these weights, as we already be saying, just to, create something good. So with this weight, we can make prediction because we have already weight, we can make prediction. And now when we make prediction with this weight, we know that it will give us something garbage, not even near to the true value. So in that case, we can say that we can make prediction. So we can see with torch inference mode. You remember inference mode, you want to make prediction. Our model text data, you can see test data X, the test. Remember here, we are pushing the X set to device. So because in the previously we haven't pushed X to device, so you can, we can say, do this X test, we can push it to device. Now we can only have X test here. Because you remember our model is on device. If it is GPU, the model is already in GPU. So you cannot send your X if it is not on GPU, it will give you an error. So here when we run this guy, now we can see here we make first prediction. So we can see we make prediction. The length of the prediction, length of prediction is 2000. Length of sample is 2000. So our X test, you can see X test, the shape, is, the length of the X test. What am I doing? Okay, on trend shape, that is the length of prediction, which is this, what we have, on trend prediction. Why do we say on trend? Because the prediction is for on trend data, because we have now started doing training. We are just doing prediction with just this with random weight. So you can see here X test on trend, which is the shape is 2000, and our original shape of length is 2000. And now this is the predictions. You can see that it gives us something -1, 0, -1. You can see this is not a good prediction, right? And for our original X test, the original level is 1. So you can see it says this is -1. Our original level is 0, it said -1. Our original level is 1, it said this. So you can see it's not giving us something correct. Our aim now is how can we update these weights so that we will start doing prediction. That is what when we do training. You can see here we have not do any training, but we just do prediction with the weight that initialized by our model. Now our aim next session tomorrow is to train a model so that it can start making a good prediction. Okay, I think we can stop here. Tomorrow we can go to the next step, set up loss function optimizer and start doing the training. Yes.
Doctor, I have a question.
Yes, go on.
So regarding this sequential, so how can you identify whether if you have a binary classification problem for your data set, how can you identify whether to use sequential method or any other method?
Yeah, so if at the basic level at this point in time, you don't need to even use classes if you don't know issue because
just to maintain
you can use sequential. There is some instances where we have what we call skip connection, for example, where you don't need to go sequential. You want to skip some layers so that you don't need to do any sequential. So we may see it later, but at the basic level, any sequential is easy for us. We want to follow from one layer to another to another. But there are some instances in deep learning where you don't want to use sequential. You want to, do some stuff. Yeah.
Okay. But mostly for binary classification, it's just a sequential.
No, not for binary classification, for anything.
For any?
Yes, for any neural network. So we are not talking here specifically for binary classification. What we are talking about, we are talking about
generally
a deep learning architecture.
Generally.
Yes. So in some architecture, you want to go linear from one layer to another to another. Okay, let me show us something. This skip connection network. So when we come to so you can see, for example, some of this deep learning architecture. What this is telling us, Okay, maybe this one. So look at this architecture. This is the input, right? Resonant. But what this is saying is that if you have an input, you skip this block, you go to the next one. Sometimes we skip, we don't go to linear. So you can see if you are skipping, for example, you can see this one input, it skipped from here, it goes to here, to output. You can see here, it skipped from here, it goes to this one. So what we are saying, like the architect, it depends on the architecture. If your architecture is linear, then you can just use NN sequential. But some architectures in deep learning, they are not linear. Do you understand what I mean? Some architectures, they are not linear. We skip, we do a lot of other stuff, and we will see more of them later.
Okay.
Yes. Any question again? All right. So I think we are good. We can continue, inshallah, tomorrow. We can finish this chapter tomorrow for this classification. And I think from tomorrow, we will have like a good understanding, like how we can train a model using PyTorch, because we now put the ingredient, everything, we just putting them together. So from tomorrow, I will see, like, we'll be able to train a deep learning network using PyTorch from end to end. Yes. All right. Any question? Okay. So in the absence of question, we see inshallah tomorrow. Bye-bye. Yeah, and please try to go through the exercise of last sessions, chapter 2, so that we can be able to see them tomorrow.
All right.
Okay, bye-bye.